the life and death of the Sun. As majestic and fiery as the Sun is, it might surprise some that it was once just a cloud of stellar dust floating through space. But how did the Sun evolve from floating dust to a fiery furnace holding the planets together, and how will it eventually end? Well, we've got all that covered in today's video, where we take a look at the evolution of the Sun. The birth of the Sun. Our Sun was formed the same way most stars in the universe are formed, from part of a molecular cloud, also known as a stellar nursery. These stellar nurseries are regions in space where matter such as gas, dust, and chemical elements needed for planetary and star formation are found. These regions are also known as nebula. The birth of the Sun began some 4.6 billion years ago, within a nebula made up of mostly helium and hydrogen and other heavier atoms found in small traces. The solar nebula that led to the creation of our Sun is estimated to have had a density of 100 particles per centimeter cube. This might be incredibly dense from our point of view, but it wasn't dense enough to cause the formation of a star all on its own. This led scientists to believe that the birth of our Sun was most likely triggered by the gravitational shock waves from a nearby supernova. The death of a nearby star going supernova sent a gravitational shockwave out into the galaxy. The shockwave hit the nebula at insanely high speeds, triggering a chain reaction of atoms violently colliding into each other. This led to a collapse inside the nebula on an atomic level. At this level of star formation, the nebula begins to spin faster as atoms collapse and condense into each other. This process continued for a few 100,000 years, resulting in the Sun's infant stage, a protostar. As a protostar, the Sun was an unstable, dense ball of hot gas, still actively pulling in matter from the nebula and growing in size as a result. The Sun spent about 100,000 years as a protostar before pressure and temperatures became stable enough to achieve hydrogen fusion at its core. With the protostar now achieving hydrogen fusion, the young Sun was spinning much faster, with an incredible gravitational pull that caused the rest of the nebula around it to be pulled in at the most prevalent angle. This caused all the gas and dust around the spinning star to settle on the same angular plane in what is known as a protoplanetary disk. While the Sun was growing in size and getting hotter, something else was going on along the protoplanetary disk as well. Forces of gravity were causing particles of ice and dust to collide and clump together. These particles clumped to form small pebbles, and as time went on, they clumped more materials, forming larger rocks, eventually reaching planet-sized objects that were known as planetesimals. These planetesimals were the infant stages that eventually gave rise to all the planets in the solar system. After about 500,000 years, the protostar had accreted all the matter it needed and began to blast out waves of intense solar wind as it became a T Tauri-level star. As a T Tauri star, the Sun spent a few million years blasting out radiation and solar wind, which cleared out the remaining shell of gas and dust around it. During this time, the formation of the planets were now competing against the intense solar winds from the young Sun. These winds are more intense closer to the Sun, and as such, planets that formed closer to the Sun are more rocky compared to the gas planets on the outer regions of the solar planet. These closer planets are exposed to more heat and solar winds, resulting in them having iron cores and less gas on the surface. On the other hand, planets in the outer regions are bombarded with less solar wind, allowing them to accumulate more gas and ice on their surfaces. Outer planets like Jupiter and Saturn were able to excrete more materials being farther from the Sun and hence grow much larger than the inner planets. All this took place along the protoplanetary disk created by the Sun, and as such, the resulting planets landed on the same orbital lane. This also explains why all the planets except for Venus and Uranus orbit the Sun in the same counterclockwise direction, similar to the movement of the protoplanetary disk that resulted in their formation. Between 10 to 30 million years after its birth, our Sun entered its main sequence phase. The main sequence phase, As a main sequence star, the Sun fuses massive amounts of hydrogen into helium. This makes it a cosmic nuclear reactor strong enough to hold all the planets together as the solar system flows through space. The Sun is so powerful that for every second, it converts over 600 million tons of matter into solar energy, which is over 4 trillion watts of energy. The Sun has been generating this amount of energy for over 4.57 billion years. In that time, it has converted about 100 times the mass of Earth into solar energy and helium. As a main sequence star, the Sun has released massive amounts of energy in the form of solar wind and radiation. These solar winds created a protective barrier around the solar system known as the heliosphere. The heliosphere shields our solar system from harmful interstellar wind and radiation that flows through the universe. Without this protective bubble created by the Sun, life on Earth wouldn't exist, as our planet would be constantly bombarded by interstellar radiation flowing through the galaxy. The fate of the planets. The Sun is already halfway through its life, and we're currently experiencing it at the peak of its stellar existence. As a main sequence star, the Sun doesn't just release its energy as solar wind, but also sends out violent rays of solar energy known as coronal mass ejections, or CMEs. These CMEs have plagued the inner solar system for billions of years, shooting out at unpredictable intervals and causing significant damage to any planet they reach. Fortunately for us, since humans began roaming the planet, there have been few planet-destroying CME bursts. At least, none powerful enough to overcome our protective magnetic field. There have been a few recorded CMEs that reached Earth, but so far they only caused minor damage, like disruption to our communications systems, and a few fires that were contained. But while Earth has been lucky to have a protective magnetic field, planets like Mercury, Venus, and Mars haven't been so fortunate. Scientists have stated that at some point over the last 4 billion years, events such as CMEs and solar flares have rid these planets of any chance of having a stable atmosphere. Even now, at the halfway point of its life, the Sun is slowly beginning its descent to oblivion. The Sun has used up half the hydrogen in its core, and from here on the Sun will gradually increase in luminosity over the next few billion years. The Sun's brightness will increase at a rate of 10% every billion years, which means a 10% increase in solar radiation and heat that blows out into the solar system. Now, what does this mean for Earth and all the other planets in the solar system? Well, a 10% increase may not seem like a lot, but it will have disastrous effects on our planet. With more heat and solar radiation being emitted from a brighter Sun, the habitable zone of the solar system will be pushed past Earth and further out into the solar system, making our current region extremely hotter. At this time, the Earth will no longer be in the habitable zone. Our oceans will evaporate and the ice caps will melt, leading to extreme greenhouse gas effects. The buildup of heat in the atmosphere will drastically raise the planet's surface temperatures, a similar process to what turned Venus into the uninhabitable planet it is today. Venus is believed to have had something of an atmosphere millions of years ago, but as the Sun increases in brightness, heat and solar radiation heated the planet's surface, trapping toxic levels of greenhouse gas in its atmosphere, turning it into the rocky inferno it is today. Over the next 3 to 4 billion years, the Sun will be 40% brighter than it is today, and Earth will have become a brown, uninhabitable wasteland with extreme surface temperatures exceeding 1,000 degrees Celsius. At this point, the 4 rocky inner planets Mars, Earth, Venus, and Mercury will all be flaming hot balls of celestial rock. Core hydrogen exhaustion. The Sun will exit its main sequence phase in approximately 5.4 billion years from now, at which point it will have exhausted all the hydrogen in its core. All that will remain will be inert helium ash that has been building up for 10 billion years. This helium will become extremely unstable, collapsing under the gravity of its own weight, causing the Sun to heat up more and grow exponentially in size. This marks the beginning of the red giant phase of the Sun's evolution. As a red giant, the Sun will expand quickly, reaching the orbit of Mercury in just a few million years and completely engulfing the planet as it continues to grow in size. Mercury's entire mass will be eviscerated in under a few thousand years. Venus will be next and will suffer the same fate. Its sulfuric atmosphere will be stripped away and its entirety swallowed up by the sun as it burns up and becomes part of the red giant. Scientists have actually observed this phenomenon where stars become red giants and swallow up nearby planets. One notable example is a red giant located some 2,000 light-years away, designated BD 48740. BD 48 is about 1.6 times the mass of our Sun and was discovered to have high levels of lithium, a rare metal that is only found on rocky planets. Scientists believe that the lithium content is a result of the red giant swallowing up a nearby rocky planet, heating the planet until it released its lithium deposits on the star's surface. This fate awaits all the rocky inner planets in the solar system. The Sun will continue its expansion, and it will eventually reach Earth's orbit, swallowing up our now uninhabitable planet and turning it into a pile of planetary ash. In about 7.5 billion years, the Sun will have expanded to over 250 times its current size, occupying Earth's current orbit, with the new habitable zone stretching from 49 to 71 astronomical units, which is already well into the Kuiper Belt. Final phase and death. The Sun will reach a phase called the red giant branch phase, and from this point on, it will have approximately 120 million years of active life left. At first, the degenerate helium in the Sun's core will ignite violently in a spectacular helium flash. More than 40% of the Sun's mass will be converted into carbon in just a matter of minutes. The Sun will then shrink to less than 10% of its current size, with more than 50 times its luminosity. The Sun will remain at this miniature stage for the next 100 million years, burning whatever helium is left in its core until it is completely exhausted. At this point, the Sun will enter its asymptotic giant branch phase, a phase where it will expand rapidly and become more luminous. This will be similar to an open flame, increasing and decreasing in size, trying to utilize whatever fuel it has left. Over the remaining 20 million years, the Sun will become extremely unstable, losing mass over a series of thermal pulses. Each pulse will occur every 100,000 years, with the Sun's luminosity increasing each time. Most people expect that our Sun will end its life in a massive supernova explosion and eventually a black hole, but that may not be the case. While the Sun may seem huge to us, it is a low-mass star compared to other stars found in the universe. Most stars that are observed going supernova have had masses of over 5 times that of our Sun. In essence, our Sun simply isn't massive enough, or has enough energy to go supernova when it dies. Instead, the final phase of the Sun will see it eject over 50% of its remaining mass into an ionized planetary nebula, much like the one that created it over 4 billion years ago. The Sun's core will be left exposed with temperatures exceeding 100,000 degrees as it becomes a white dwarf. This white dwarf will be the final resting phase of our Sun, a super-dense dead star with more than 50% of the Sun's present-day mass, but barely the size of Earth. The planetary nebula around the white dwarf will disperse in about 10,000 years, but the white dwarf itself will survive for trillions of years. Some theories state that the white dwarf will eventually fade into a super-dense black dwarf, or even a black hole. Alternate endings. If our Sun somehow had 10 times its current mass, then the final phase of its life would end in a massive supernova explosion that would sweep through the solar system in less than 8 minutes, destroying everything in a 10 light-year radius. The energy released from this supernova would outshine the galaxy for a few minutes, leaving behind a new nebula. What would be left behind would be a rapidly spinning neutron star that may eventually collapse into a black hole. So, do you think our Sun will fade away quietly into the darkness of space, or go out with a bang of epic proportions? Let us know in the comments below, and we'll see you in the next video.